Good evening, everyone. I hope you can hear my voice. Am I audible? Can you see the
Audible,
screen?
ma'am. Audible,
Okay,
you can
fine,
speak.
fine. Good evening, everyone. On behalf of Unique Measurement Service, I warmly welcome you all to our free webinar on GD&T basics and applications. Let me introduce myself. I'm Dr. Gifty Evangeline here, General Manager of Unique Measurement Service, your host for today's session. We are truly excited to have participants from various regions and industries joining us today. Your presence shows your commitment to continuous learning and professional growth, and we appreciate you taking the time to be here. Last session, nearly 200 plus participants were being benefited in the basics of GD&T. So in case, if you have been missed out our sessions, you can definitely log into our community group. So where we have shared our link and you can watch through in the YouTube also. Before we begin, a few quick points. Please ensure your mics are on mute during the session. If you have any questions, feel free to post them in the chat box. We will address them during the question and answer session at the end. The session will be recorded and the link will be shared with you after the webinar. A short note on Unique Measurement Service. Unique Measurement Service is the largest industrial measurement and calibration testing scanning service provider in India. We were established in 2015, which has been nearly 16 branch offices and been headquartered in Chennai. Our services, CMM inspections, portable CMM arm type on-site inspections, laser track inspection, calibration, reverse engineering. We also provide advanced level of metrology training courses. Vision 2030. So nearly 10,000 plus engineers freshers training. We have a plan for the Vision 2030. As of now, nearly 30 plus skill development workshops has been conducted and almost trained nearly 500 plus professionals across India. So Unique Measurement Service is known for deep industry insights. So at UMS, we have well-versed trainer. So let me introduce them without further delay. So Mr. Tamil Paradhi and Joshua, I'm pleasure to introduce them. They are the expert speaker for the day. So they will be sharing the seasoned professional knowledge and extensive experience in metrology with you. So last week we have went through it basics of GD&T. So why GD&T is important to us, and across the GD&T, last session we also went for the real world users cases. So today's sessions, what we will be learning is tolerance of orientations and tolerances of location. Apart from this, we also have advanced level of GD&T training programs. So it is either in online, offline, hybrid modes we have. It's been tailor mode into 15 hours to 40 hours sessions with the practical experts. We can share the knowledge where we can make them the trainees, not only freshers as well as it will be advanced level for the experienced professionals. So there will be end of the session, there will be a question answer interaction. You will also have the feedback session at the end. Without taking much delay, I'll welcome Mr. Tamil Paradhi and Mr. Joshua to take over the session so we can directly go to the GD&T advanced level of training. So over to Mr. Tamil Paradhi and Joshua.
Good evening, everyone.
Last week we have seen topic basic quality concept for understanding GD&T, and then we have covered form. So I'm going to recall in form, and then I will continue the pending GD&T topics. So here straightness is the condition where element surface or an axis is a straight line. So here we're going to check in a surface in one linear direction, and we're going to check the waviness is whether it is above the tolerance zone or it is below. If it is in below, then it is within spec. If it went outside the zone, then it is out of spec. So this is the scenario of straightness in a cylindrical job. So here also same condition. In one particular cross section, we can get a straight surface in a cylindrical job. So here we're going to check the straightness. Here the manual method will be a dial gauge. So the feature cylindrical feature is arrested in a V block or any other clamping phase. So the part is set to be move. Part or dial gauge is set to be move in a linear direction. So the variation will be noted in a dial gauge. And if the variation is below this tolerance, then the part is okay. If it goes above this zero point 0.1 tolerance, then the part is out of spec. So next here, flatness. So the flatness is also same like straightness. Here we're going to check the entire surface. So we'll be cover two cross-sectional area. So the tolerance here, the tolerance will be acting as a two parallel plane. So this is the manual method. The dial gauge will be move in two linear direction. So the reading will be noted in straightness. It will cover only one linear direction. Here it will cover two linear direction of waviness. So next is circularity. So it controls the circle form is called a circularity. Here in a cylindrical feature, in a particular cross-sectional area, we'll get circularity. So the waviness of the circle must be lie within this two concentric circle. The two concentric circle is derived from this tolerance point 1, plus off and minus off. So the waviness will be within this concentric zone. So here the manual method for circularity is the part is clamped in a V block or any other clamping picture, and then the dial gauge is placed in a part and set at 0, and then the part should be rotated in a 360-degree, so we can get the reading of the circularity. So next is cylindricity. Same like circularity. So here we're going to cover the entire area of the cylinder. So here the manual method will be the part is said to be rotate, and as well as it should be moved in a linear. So here the straightness will consider. In circularity, straightness will not be considered. Only the circular waviness will be considered. In cylindricity, we're covering both the entire cylinder. So the straightness as well as the circularity waviness is considered. Okay. Next, we're going to continue the topic from tolerances of orientation.
Hello, Joshua. This is Tamil Pardi.
Yeah.
Actually, I need some information about some form tolerance classes. So I will ask some basic questions. It will helpful to clear
Sure.
some clear picture. Okay.
Okay.
Is there any manual method for checking straightness or flatness? And
Yes.
how we are going to check by using manual methods?
So the manual method will be a dial gauge. Here in this image, you can see. So with with this 3 jig, we will level the plane. So the surface plane will be at level. So after that, we will check reading with the dial. So the dial will be placed in a surface where we're going to check flatness, and then the dial will move in two linear direction. So the reading will be noted
Okay.
in a dial gauge. So the reading must be below this tolerance zone.
Okay.
So are
Then
we
one more
clear?
question.
Yeah.
Yeah, yeah.
Okay.
And what is the difference between straightness and flatness? Some
Okay.
major differences and some somewhat minor or major difference.
Yes. In straightness, only one linear direction the dial will be travel. In flatness, two linear direction we're going to travel. So in straightness, one linear axis waviness will be covered. So in this plane, if we check straightness, we will move in one linear direction. So the one linear waviness will be covered. In flatness, we're going to check the entire surface. So the dial gauge will move in the entire surface. So we can get the entire surface reading. So this is the major difference between straightness and flatness. The concept will be same.
Okay, it's clear now. So some basic questions is there. One more question. And
Yeah.
why form does not have datums?
Yes.
So why
Okay.
we called as it is a independent, it is not dependent. So what
Okay.
is the purpose?
Here we're going to control the individual feature, formation of the feature. For formation of the feature, no other feature will be dependent. So here, without any dependent, we're going to check the same feature formation. So no other feature needed. So it is independent. So for other GD&T and all, we need some reference feature to control the feature. So here only the feature formation will be controlled. So no any other feature will need. So no need of any other feature. You get it?
Yeah, thank you, Joshua.
Yeah.
It's clear now. Please go ahead.
Thank you, Tamil. Okay. Now we're going to continue this session with tolerances of orientation. So in tolerances of orientation, three parameters will come: angularity, perpendicularity, and parallelism. So we begin with angularity. So here you can see the drawing at left column. So here for this feature, we're going to check the angularity with respective to the datum A. You can see this feature control frame. So 0.3 is the tolerance, datum A is the reference feature. So here the angularity is a planar feature. Other than 90 degree, we're going to check the reference plane is within the tolerance with respective to datum. So here the scenario, for this scenario, the tolerance will be act as a two parallel plane because the feature is a surface plane. Here in 3D view, you can see clearly. So the overall tolerance will be 0.3. Here, the part is said to be angled in a fixture or in a sine bar, and then a dial gauge will be moved like this. In an entire surface, the dial gauge is said to be moved, and then the reading will be noted. And the angular deviation must lie within this 0.3 tolerance zone. in top right corner, you can see the setup. So they're rotating a part in a 60-degree angle so that the feature we used to check will be lies in a straight area so that we can check in a dial gauge, or we can create angle in a sine bar and then arresting datum in a sine bar. We can get the angular area in a flat surface. Like that also we can check. So here in this scenario, left hand side, the angular deviation is within the spec, within the tolerance zone. So it is within the spec. Here, right hand side, the angular deviation is more. So it went outside this tolerance zone. So it is out of spec. So next, this is the scenario where we're going to check a cylinder axis with respect to the datum plane. So here, this whole axis, we're going to check angularity. The angle is 60-degree. So you can see in this 3D image, the tolerance type is a cylindrical tolerance because the feature is cylinder. So the tolerance will be act as a cylindrical tolerance. So here the deviation must be lie within this cylindrical zone. Here the left one is within spec, and right side the angular deviation, because of the more angular deviation it went outside the zone, so it is out of spec. Okay. Next, this is other scenario. So here the axis is also the feature is also a axis, and then datum is also a axis. So the angle will be 45. In right side drawing you can see here the tolerance zone will be a cylindrical tolerance zone because the feature is cylinder. So the zone will be oriented 45-degree with respect to the datum axis. And then this angular deviation must lie within this zone. So you can see the left side picture, the axis, the whole axis is lying within this zone. So in right side, it went outside the zone, so it is out of spec. Next one, perpendicularity. Here at left side, you can see the drawing. So in perpendicularity, the feature must be in a right angle to a reference datum. So that is the concept of perpendicularity. Here you can see the feature control frame. Point 3 is the tolerance, datum is A. So bottom surface is the datum A. So here the feature is plane, so the tolerance will be act like a two parallel plane. You can see in this picture clearly. So with fixture or a 90-degree tri-square, the datum must be arrested, and we can get the feature flat. So there the dial must be placed and set at 0, and then we can move the dial into linear direction. In this GIF video you can see, and then the angular deviation must be noted. So here the angular deviation is more, it went out of the spec, so the part will be rejected. So the part is not a perfect right angle to datum. Here this is the other scenario. Here for this whole axis we're going to check perpendicularity with respective to the datum A. Datum A is bottom plane. Same the whole axis must be 90-degree to the datum A. But here the zone will be cylindrical because the feature is cylinder. So same as before, the axis, the angular deviation must lie within this zone. So here left side, it is angular, but it is within the zone. So it is within spec. So in this right side, it is more deviated and went above this tolerance zone, so it is out of spec. So next one, parallelism. So here in this picture, top plane they are asking parallelism. 0.3 is the tolerance. Datum is A, which means bottom plane is the datum. So parallelism is the feature where with respective to the datum, it should maintain equivalent or 0 degree. So the feature must be equivalent or 0 degree with respective to the datum. So here the feature is plane, so the tolerance will be the two parallel plane. So next here, same the manual method will be, the dial gauge is set at 0 and the datum will be arrested. So the dial gauge will move in two linear direction and the reading will be noted. So here right side is more angular, so it is out of spec. So the left side is within spec. It lies between this tolerance zone. So this is the scenario where the datum is also axis, the feature is also an axis. So the feature is a cylindrical hole. So the datum, the tolerance will be circular, cylindrical tolerance zone. You can see in the 3D image how the tolerance is hacked. So here in the side view, you can clearly view the angular deviation. So in left hand side with respective datum axis, it is parallel. So the angular deviation is within this tolerance zone. So it is within spec. And at the right side, it is more deviated. So it went above this tolerance zone. So it is out of spec. Okay. I hope you understood this orientation.
Yeah, sure. Can I ask one question?
Yeah, sure, you can ask.
Yeah. Yeah, sure. What is the difference between angularity and perpendicularity?
Yeah. In angularity, we can measure, we can control any given angle in the drawing, except 90 degree or 0 degree. We can control any other angle. So in perpendicularity, we going to control the feature 90 degree only. Right angle only we will control. So in angularity, we will control any given angle in the drawing. So this is the major difference. Working principle all are same.
Okay.
Okay, any other doubt you have cleared?
Please continue.
Yeah, thank you. Okay, next tolerances of location. So in tolerance of location, we have three parameters, true position, concentricity, and then symmetricity. So this three is the same concept. So only a little difference will be there. Okay, here this is the difference. There is a different tolerance zone in position, depends upon the feature. So first one for cylinder, it will be a cylindrical tolerance zone. If they ask position for plane, then the tolerance zone will be parallel plane. If they ask position for a spherical feature, then the tolerance zone will be spherical. That blue highlighted area is the tolerance zone. So you can see the drawing for the center hole. They asking position 1.4 is the tolerance. Primary datum is A, the top plane, and the secondary datum is left side plane, and territory is datum C. Okay. The basic definition of position is
total permissible variation that a feature can have from its true position is that exact coordinate defined by basic dimension or other means that represent as a nominal value. So in other word, the geometric dimensioning and tolerancing position is how far the feature location can vary from its true exact theoretical position. So with respective to the coordinate, we're going to check this hole is located correctly or not. That is the basic concept of position. So here we're going to check cylindrical hole. So the tolerance will be cylindrical tolerance. You can see in this 3D image. So with respective to this datum, the origin point will be in this corner. So from this origin point, x-axis, the x coordinate is 10 mm and then the y coordinate is 10 mm. So here this is a zoomed view. Here this is the theoretical true position, exact theoretical true position. This is the offset deviated from the theoretical position. So here the x deviation is called as del x and the y deviation is called as del y. So we're going to calculate the overall deviation. The overall deviation is z. You can see here. So we can move on to the formula. For true position, formula is there. Z is equal to 2 into square root of del x square plus del y square, where the z is overall deviation. So del x is x measured deviation, and del y is y measured deviation. So the measured deviation will be calculated by the difference of nominal and actual. So the difference is the measured deviation. For example, for this coordinate 10 mm, here the actual is 10.4. So the deviated value is 0.4. So for this y-axis, here the actual is 10.3. So the deviation is 0.3. So here we're going to substitute this deviation in this formula. So z is equal to 2 into x. Deviation x is 0.4 and deviation y is 0.3. So if we calculate this, we can get a value like 0.98. So it is below this 1.4 tolerance. So the position is within spec. It can easily fit. So by calculating this formula, we can find this position. So now we're going to see the position with modifiers, MMC modifiers. So they will mention MMC or LMC. If MMC, they will mention here M, or LMC, they will mention L. So first we have to know for a hole and shaft, what is MMC, what is LMC. MMC is the condition where the material will be maximum. LMC is the condition where the material will be least. This is the key point. So here at left hand side is the hole. It is a hole. So for this hole, MMC will be 13.5. So here you can see the diameter 14, plus or minus 0.5 is the tolerance. So the range will be 13.5 to 14.5. Here when the hole is reducing, the material will be increased. Material will be maximum. So when the hole gets smaller, the material will be maximum. So the smaller range is the MMC. In this range, 13.5 is MMC. So the smallest allowable diameter will be MMC in hole condition. So the LMC will be the largest allowable diameter. So the largest range is 14.5. When the hole gets bigger, the material will be reduced. So the material least material will be there. So it is least material condition. So for the shaft, it is opposite. So when the shaft gets larger, the material will be in maximum. If the shaft dia get smaller, the material will be in least condition. So here you can see for shaft MMC is 14.5, the largest allowable dia. LMC is 13.5, the smallest allowable dia. Now with this MMC modifier, we're going to calculate the position. Here this is the scenario. They're asking a position for this hole. So the position tolerance is 0.1. So they have given MMC. We have find out that position. The actual position is 1.8. So it is out of spec. Without modifier, we have checked the actual position is 1.5. So now we're going to check with MMC condition, maximum material condition we're going to see. So here for this hole, MMC will be 13.5, LMC will be 14.5. So at the right side picture, you can get a clear view. So here the largest dia is 14.4, the actual diameter, where the manufacturer manufactured a dia for 14.4. So the MMC dia is 13.5. Here you can see the MMC dia. So the dia should be in 13.5, but the manufacturer uh, increased the hole size, so it has more possible uh, to assemble the part due to the largest dia. So due to the larger dia, we can get a clearance. Here you can see the clearance. Because of the clearance, the part will assemble easily. So here we're going to find out this clearance. Clearance is bonus. So technically we can say it as bonus tolerance. So the bonus tolerance is calculated by actual dia minus MMC. So if we find the difference, we can get this clearance value. So here BT means bonus tolerance. Bonus tolerance is equal to actual dia minus MMC. So here the actual dia is 14.4 and MMC is 13.5. So the bonus tolerance will be 0.9. So this bonus tolerance will be added to this GD&T tolerance. So 1.9 is the overall tolerance for MMC in this diameter, for this diameter. If the diameter changes, then the bonus tolerance will be changed. So for this 14.4 diameter, the bonus tolerance will be 0.9, and this, that 0.9 will be added in this GD&T tolerance. So position tolerance for MMC at 14.4 will be 1.9. Therefore, the actual position is lesser than the theoretical position. So the actual position is 1.8. Theoretical position for MMC condition is 1.9. So it is lesser. Therefore, it will assemble in a part, assemble easily. So therefore, the part is okay in maximum material condition. Okay. So same like if LMC also same, if they given LMC, we're going to take LMC value. That will be the difference. So here now we're going to see the topic with composite tolerance. Composite tolerance with position. So here you can see the position. They are asking two positions in a same feature. If they given like this, it is called as composite tolerance. I will explain you. So top position is same as we seen below above. Same procedure, but composite tolerance there is a rule. So wherever the pattern is there, mostly they will ask this composite tolerance, which means it has some rule. So this pattern must can go right side. This is the tolerance zone. So within this tolerance zone, the pattern can move right side and the pattern can move left side without disturbing this pattern dimension. 50, you can see 50 for X and 40 for Y. Without disturbing this pattern dimension, it can move left, right, or up and round, and also it can move diagonally like this. Also, the pattern can rotate without disturbing the pattern dimension. Within the tolerance zone, it can rotate. But this is not allowable. So here, this hole is located here, and here this hole is located here. So it is breaking this what pattern dimensions. So this is not allowed in this composite position. So position get completed. So now we're going to see concentricity. So for concentricity and position is similar. Only one variation is there, where if the datum and feature axis are in same inline, then they will have concentricity. So the definition also same, where with respective to the datum, the feature axis should be in same inline. We're going to check how variation from the datum axis. So the formula will be same like position. So here we can see. So the tolerance zone will be cylindrical because we're going to check cylinder feature. So here you can see the red dot is a derived position. It is within this tolerance zone. So in a straight view, you can see at the right side. So the exact center point is here. The dotted line center is a actual. So it variation. So it has some offset in x and y. So same like position, the deviation x will be calculated, and then the deviation y will be calculated and then substituted in this formula. So if the overall deviation is lesser than this tolerance, then it is located below this zone, tolerance zone. This red area is the tolerance zone. If it is greater than this tolerance, the value is greater than this tolerance, then the deviation went outside this tolerance zone. Same like position. Okay, now we're going to see symmetry. So here there is a drawing. So here it has condition. For example, if the datum is given directly here, then this plane alone will be datum. If they extended like this, and then the distance dimension they have given, then the feature mid-axis should be taken as a reference. So you can see here they have extended a leader line, and then they have given dimension for this thickness, and then there they have given datum. So in this condition, we're going to take reference both center plane will be the axis. So the datum axis will be the center for this, and this plane will be the datum axis. And here same as for feature, they have extended, and then dimension has been given, and then they have asked symmetry for this feature. So the reference will be the center to this, and this feature axis will be the center axis. For this center axis, we're going to check symmetry. It should be within it should be same in this axis. So here you can see the 3D image. The dark red portion is the actual center plane. The tolerance has been divided by two parallel planes. Here the offset will occur in one direction only, whether it will go up or whether it will go down. So here the side view, you can see the tolerance zone, and then derived actual position. So same like position and concentricity, the offset value is noted, and then here only one deviation will be there. So only del x will be there. So the offset value will be substituted here. The overall deviation z is lesser than this tolerance, then it is located in within this tolerance zone. If the overall deviation is greater than this tolerance, then the derived point went outside this tolerance zone. Okay, this is the basic topic of orientation and location. Okay, from this topic we can wind up. We can continue another two topic, profile and runout, in next week's section.
16th International Machine Tools Exhibition, ACME 2025, which has been held from 19 to 23rd June 2025. So tomorrow and Monday we will be available in the stall number 108, Hall H. So you can come over there and you can meet us directly and you can have a direct session with us. கைண்ட்லி ஷேர் யுவர் ஃபீட்பேக். உங்களுக்காக ஒரு ஸ்மால் கொஸ்டின் ஆன்சர் செஷன் மாதிரி ஒரு கூகுள் ஃபார்ம் இருக்கும். ஸோ நம்ம என்ன இன்னைக்கு நம்ம ஸ்டடி பண்ணோன்றதுல ஜஸ்ட் உங்களோட ஒரு செல்ஃப் எவாலுவேஷன், தட்ஸ் இட். உங்களுக்கு என்ன அண்டர்ஸ்டாண்டிங் ஆயிருக்குன்றதுக்காக ஜஸ்ட் அதை மட்டும் பார்ட்டிசிபேட் பண்ணுங்க, உங்க ஃபீட்பேக்கை கொடுங்க.
இதை ஸ்கேன் பண்ணியும் நீங்கள் ஃபீட்பேக் கொடுங்க. நான் ப்ளஸ் கமெண்ட் அந்த செக்ஷன்லேயும் போட்டிருக்கேன், நான் ஃபீட்பேக் லிங்க்கு. ப்ளஸ் கம்யூனிட்டியில் ஆட் ஆகணுன்னா அதோட லிங்க்கும் ப்ளேஸ் பண்ணியிருக்கோம், நீங்கள் செக் பண்ணிக்கலாம் இன்பாக்ஸில்.
நெக்ஸ்ட் டைம் உங்க கொலீக்ஸ் அதே மாதிரி உங்க டீம்ல ஃப்ரெஷர்ஸ் யாராவதுலாம் இருந்தாங்கன்னா டெஃபினட்டா அவங்களையும் பார்ட்டிசிபேட் பண்ண சொல்லுங்க. கண்டிப்பா இது ஒரு வேல்யூபிள் செஷனா உங்களுக்கும் இருக்கும். மோர் ஓவர் ஹை ஓப்பனிங் செஷனாவும் இருக்கும். ஸோ தேங்க்யூ ஸோ மச்.
தேங்க்யூ சார்.